So this will be a session on artificial neural networks, as already mentioned. So I would like to know one thing from you, like what is your experience in this topic? You have previously implemented artificial neural networks, or I mean, any machine learning models have you implemented, any of you? Do you have some basic idea, or do you not have any idea? I would like to know this point. Yes. Any of you have zero idea about artificial neural networks?
The few sessions are already covered on artificial neural network.
Artificial neural networks you have studied previously, right?
Yes, yes, sir.
Achha. So you must be knowing the basics of artificial neural networks, all of you. So
Yes,
let us go through the topics once again. Okay. So I am sharing my screen. If you can see it, kindly let me know. So my screen is visible?
yes, sir.
Okay, thank you. So I'm turning off my camera so that I can present in full screen mode. Okay. Okay, so since you have already studied artificial neural networks, let me try to go into some mathematical part of that. Before that, I have few slides on what is artificial neural network, but I feel that you already know these things. I mean, to be very precise, it is inspired from biological neural network, that is human brain. So what is the difference? The main point that we have to remember here is we can do lot of tasks simultaneously, like perceptual task, recognition task, etc. But artificial neural networks, we can train to perform only very specialized tasks. For example, one neural network can do only face recognition. It cannot do maybe other object recognition. So that is the main difference between biological and artificial neural networks. Okay, and why that difference is coming? Because this biological neural network is highly complex. It has massively parallel architecture of neurons, which is very difficult to realize with artificial neural networks. Okay, so some important functions, although I mean I think these are covered, but just as a starting point. So exploits nonlinearity. Artificial neural networks are used for function mapping. So some input is mapped to some output based on some function. We try to estimate the function using artificial neural network. So exploits nonlinearity means that function can be a nonlinear function. So the output can be non-linearly dependent on the inputs. Next, adaptivity means we can adapt the network based on the surrounding environment. So if the environment changes, we can adapt the parameters of the network so that it responds better to the changed environment. Next, evidential response, which means that artificial neural networks can make some prediction with a confidence level. So it not only makes a prediction, but it also says I am making this prediction with this much confidence. So next, fault tolerance. Artificial neural network must be fault tolerant, which means if some of the components inside the network fails, the entire network should not collapse. So it should still be able to work if few components fail. Okay, so with this brief introduction, I am going to introduce the first artificial neural network that was developed by McCulloch and Pitts. It was proposed in 1943 And next came Hebb, postulated the rule of self-organized learning in 1949. Then 1958, Rosenblatt proposed the perceptron model. So first one is McCulloch and Pitts model, and they are, this idea that neural networks can be used as computing machines was first introduced. So and this model is very simple. So basically, if you see this diagram below the slide, so there is a computational unit in center shown as a circle. So what it is doing, it is taking certain inputs denoted by x1, x2, xn, and it is giving an output y. Okay, so this model has some limitations. For example, some are stated here in the slide. So the artificial neuron accepts only binary inputs. So inputs cannot be any real number. So it has to be some binary input like 0 or 1. And this produces a binary output based on certain threshold value. Okay, so this computational unit, what it does, it aggregates these inputs. So inputs are zeros or ones. These are combined in some using some aggregation, and then this combined summation is passed through some threshold block. Okay, and this threshold, the value of the threshold needs to be adjusted. Okay, so this is mainly used for classification, this model. And what we have to finally decide to realize certain function, so we need to we need to get this threshold value, as well as there is one more thing that we need to know, these inputs x1, x2, xn, we can call them either inhibitory or excitatory. Okay, inhibitory means the inputs, the inhibitory inputs means like whatever inputs are coming, basically negation of that comes into the computational unit. And excitatory input means whatever inputs are coming, that straight away goes into the computational unit. So if we look into some problem, it will be more clear to us. Let's try to realize this AND function using McCulloch-Pitts neuron model. So AND function we all know. So if the two inputs x1, x2 are, any one of the two inputs is 0, the output should be 0. And if both the inputs are 1, the output should be 1. Okay, so now McCulloch-Pitts model, how training is done for this model? It is done using trial and error method. So unlike other neural networks, more advanced networks, here we do not have any backpropagation or adjustment process, weight adjustment process. So this works with trial and error. So first, one first trial is if both the inputs are excitatory. What I said, excitatory signal means the inputs will come to the computational unit as it is, and inhibitory means the input should be negated, that is, it is multiplied by -1. So if we consider both the inputs as excitatory inputs, so we can see x1, x2, both of them will be multiplied by +1. So if we look into the diagram here, so x1 multiplied by +1 and x2 multiplied by +1. So these are summed up inside the computational unit, and the summation is denoted by S. Next, we pass this signal through a threshold block. If S is greater than theta, we output 1, and if it is less than theta, we output 0, or greater than equal to theta, we output 1. If it is less than theta, we output 0. So if we pass, if we consider both signals as excitatory, we can see that when we feed x1 equals to 0, x2 equals to 0, the summation S is 0. So 0 into 1 plus 0 into 1. When we feed the second pattern, x1 0, x2 1, so 0 into 1 plus 1 into 1, basically 1. So S is 1. So when we feed the third pattern, the summation is 1, and when we feed the fourth pattern, the summation is 2. So now we can see if we set the threshold theta, threshold block as 2, that is, if theta is summation is greater than equal to 2, we will map it to +1. If the summation is less than 2, we will map it to class 0. Then we can clearly see that this model can realize the AND function. So if both the inputs are excitatory and the threshold is set to 2. So this works with trial and error method. So given any function, what we have to, how we realize that function using McCulloch-Pitts model, we try with all possible combinations. Both the inputs are excitatory. If it doesn't work, so if we cannot find any threshold which can do the mapping, then that combination doesn't work. Then we go for one as inhibitory, one as excitatory. Second trial method. So if it still doesn't work, both inputs can be considered as inhibitory. So using this trial and error method, finally, we should be able to get the appropriate combination of weights, that is inhibitory, excitatory, and the threshold block. Okay, so but very important point is that, so what type of function this model is learning? Basically, it is learning some linear function. So x1 multiplied by some weight w1, let's say, plus x2 multiplied with some weight w2. So this summation we are checking. If it is greater than theta, then it is mapped to one class. If it is less than theta, then it is mapped to another class. So basically, w1x1 plus w2x2 equals to theta is the separator, which is a equation of a straight line. So this function is, this model can learn only straight lines. In 2D. If we consider 3D, it can learn only linear planes. In multidimensional, it will be linear hyperplane. So any nonlinear function cannot be learned using this model. That is one of the important limitations of McCulloch-Pitts model. And further, it cannot accept any input which is non-binary. That is, input has to be 0 or 1, output also has to be 0 or 1. So verify, this you can take as an exercise. Verify if you can solve AND function with at least one inhibitory signal. In this slide, we consider both as excitatory. So if we consider one as inhibitory, one as excitatory, so basically one of them will be multiplied by -1, another will be multiplied with +1. Then you can verify that AND function cannot be realized using McCulloch-Pitts model. So all the simple logic gates which are linearly separable, like OR, NOT, NOR, NAND, and etc., can be realized using McCulloch-Pitts model, but XOR cannot be realized because XOR is non-linearly separable. If both inputs are same, the output is 0. If both the inputs are different, output is 1 for XOR. So it is a non-linearly separable data, and a McCulloch-Pitts model cannot realize the XOR function. Okay. So any question regarding McCulloch-Pitts model? Any questions? Okay. So let's proceed. I'm going a bit fast. If you fail to understand some point, please stop me. So next model that we will learn here is single layer perceptron. So as I said, first 1943 this McCulloch-Pitts model was proposed. Then this came in the 1960s, single perceptron model. Okay. So there are three terms here: single layer perceptron. So perceptron is the name of the neural network. Basically, like the previous one we called as McCulloch-Pitts model, this we call as perceptron. Single layer part we can come after some time. Okay, so the advantage of perceptron over McCulloch-Pitts model is now we remove the dependency on binary inputs. So now our inputs can be any type of real numbers. So it need not be only 0 and 1. We can feed any real number as input to a perceptron. Okay, so it is the simplest form of neural network used for classification of linearly separable patterns. So once again, it also like McCulloch-Pitts model, here also we deal with linearly separable patterns. So we cannot realize non-linearly separable data using single layer perceptron. We cannot separate them. Okay, so how it works, let us see. So it consists of a single neuron with adjustable synaptic weights and bias. This is another difference from McCulloch-Pitts model. In McCulloch-Pitts model, we have either inhibitory or excitatory weights, and they are not adjustable. We have to fix whether a weight is inhibitory or excitatory using trial and error. But here we are writing the term adjustable. So there is some way to modify the weights of the model. So the algorithm that is used to adjust the free parameters are basically same as weights and bias. So the parameters that can be adjusted are called free parameters. So first appeared in a learning procedure developed by Rosenblatt for his perceptron brain model. So he proved here that if patterns are drawn from two linearly separable classes, then the algorithm converges. And the for 2D it will be a straight line, for ND it is decision surface. So the decision surface is placed as a hyperplane between the two classes. So if we have linearly separable data, that means we have two classes which are linearly separable. In that case, the perceptron algorithm converges and positions the decision surface in the form of a hyperplane. Okay, so one perceptron built around a single neuron means if we have only one neuron, then we can separate two classes. So if we deal with a multi-class problem, we need more than one neurons basically. So any one neuron can only separate two classes. Okay. So next, how this single layer perceptron model is trained, or what algorithm is used to train the perceptron, that we are going to discuss. So before that, we need to understand some optimization techniques which are used to train adaptive filter. So what is adaptive filter? Next we are going to discuss that. So once we learn adaptive filter, we can easily understand how single layer perceptron works. Okay, so adaptive linear filtering. So the words are very understandable itself. So adaptive means something that can be adjusted. So as we said, neural networks must have the property to adjust based on the environment changes. So adaptive means that. So there are certain free parameters, the adjustable parameters inside the network, which can be adapted basically. So then linear filtering. So this is linear means like single layer perceptron can draw a straight line. So adaptive filter also we are talking about linear adaptive filter, not non-linear filters. Okay. So now let us consider one system, which is unknown, like it is written as unknown dynamical system. So what it means basically, we do not know the mathematical characterization of this system. Okay, what we only know is it can accept a set of inputs as given in the figures, x1, x2, xm. There are m different inputs to the system. These are somehow combined inside the system and output is coming out of the system. Output D is coming out. So I is the, we can call them it as the, epoch or some pattern number. So first pattern is I equals to 1, second pattern means I equals to 2 and so on. Okay, so we have a set of inputs which is m dimensional, which comes into the system and it is giving some output D. And how this output D is related with the inputs, so that is unknown. So when we deal with neural network training, or when we have some real problem in hand, we talk about data, right? So we have some data set. So data set gives a set of features and the output class or the output value. So let's say if we want to do dog versus cat classification. So we have two animals, dog and cat. We want to differentiate between the two. So dog is represented as an m-dimensional vector of real numbers. Cat is also represented as a m-dimensional vector of real numbers. So somehow this representation is done. Either we can take some specific features from the dog image, let's say height of the dog, or weight of the dog, or whether the dog has the color of the dog. So these are certain features, or we can pass it through some encoder and get the encoded features. So finally, from a dog image, we have m-dimensional real number which represents the dog. From some cat image, we have a m-dimensional representation which represents the cat. So this m-dimensional representation is fed at the input of this dynamical system. Okay, so only a set of input-output patterns is available. That means for this m-dimensional input, the output is dog. For this m-dimensional input, the output is cat. So like this, we have several patterns. We call them as patterns. So this is available. So if this feature is m-dimensional, then we have m inputs to the system. And without loss of generality, let us assume there is a single output. If there are multiple outputs, the same algorithm can be applied for all the outputs. Okay. So this is the external behavior of the system. We can define in this way. So I is the pattern number. I is m-dimensional pattern. As I said, it's written as x1i, x2i, up to xmi. Di is the desired response. For this pattern corresponds to what? So either it can be this size can be distributed spatially. For example, as I said, cat, dog, it is an image. From image you can come up with this vector, or it can be some distributed at time. Say from previous 5 days temperature, we are trying to predict what is tomorrow's temperature. So m is 5. Previous 5 days temperature, we put in xi, 5-dimensional input, and di is tomorrow's temperature, that is 1-dimensional. So basically our problem is to design multi-input single output model. So how we design, let us come to that. So so steps in training adaptive filter. So the two terms, adaptive filtering. So what happens normally, we initialize the system randomly. This unknown dynamical system that we are talking about, we initialize them randomly. For example, if we look into this figure again, so this x1, x2, xm, what is initializing the system? So these inputs do not directly come inside the system, rather they are multiplied with some factors, some weights. Each input has certain priorities that are represented by the weights. So x1 is multiplied by some weight, say w1. x2 is multiplied by some weight, say w2. So for m-dimensional input, we have m such weights. So this combined information, x1 multiplied by w1 plus x2 multiplied by w2 and so on, this comes inside the unknown dynamical system. And based on that, some output yi is produced. So output, so since we have initialized the system randomly, w1, w2 are randomly initialized, the weights. So output that is produced by the system need not be exactly equal to di. So because the weights are initialized randomly, some different output can be produced, whereas the desired output that we want to get is di. So there is some error at the output of the system. So this error is used to make some adjustments to the free parameters. So this error signal ei is obtained by comparing the output signal yi with the desired response di. And based on this error, we will devise certain, or we will learn certain algorithms that automatically adjust the free parameters. So some free parameters we initialize randomly. So these parameters are now adjusted in accordance with the error signal, so that the adjusted parameters works better in fitting the input to the given output DI. Up to this, any questions? Anyone has any questions?
No, sir.
Fine. Okay. So now, so let us understand the algorithm. So basically, as I said, each inputs are multiplied by some weights W. So they do not come directly; they are multiplied by some weight W. So these are combined to get some output VI. By output of the system is VI. See, these are notations that we are defining. This VI is next passed through a linear filter. So because we are dealing with linear adaptive filtering, so this is basically yi equals to vi, its identity mapping. There is linear filter we have just placed here to understand that this is linear filtering. So yi equals to vi here. So it is in this particular case there is no use of this linear filter. So if it is a nonlinear filter, then vi is mapped to some nonlinear function, but in this particular case yi is equal to vi. Okay, so what input is coming inside the system? If we see that this each weight is multiplied with corresponding x, and there are m such inputs. So k equals to 1 to m wki xki. So wk is this subscript 1 to m, k varies from 1 to m, that is the summation. So weighted summation of the inputs comes inside the dynamic system, and this is directly passed out of the system as vi. Then vi is passed to the linear filter, we get yi. So yi is same as this summation. Okay, now this can be written in matrix form as like this: xk transpose I wki. This same summation is written in matrix form. Okay. Sorry. Okay. So basically, if I can explain here, so this xk we are talking about, this is basically a vector x1, x2 up to xm. So this is a m-dimensional vector, and the weight vector that is associated is also m-dimensional, w1, w2 up to wm transpose. Okay, so what we are doing, we are multiplying w1 with x1 plus w2 x2 plus up to wm xm. This is fed in, this is the output of the system. So if we, we can also get this if we multiply these two matrices, right? So this is what is written here, x transpose w. So x transpose basically makes this as a row vector. It is a column vector. So this becomes x1, x2 up to xm. This is transpose, means it is a column vector. So w1, w2 up to wm. So this summation of xi wi can be written in matrix form as x transpose w, xk transpose wk. So hopefully this matrix notation is clear to all of you how it is coming. Okay, so now so this is the output predicted by the model, whereas the actual output is di. This di is the desired output. I have not written it in my slide. So this is basically the output predicted by the model. This is yi. Desired output is given, in the data set, that is d. So basically we are making some error, that is desired minus what we are predicting, error. So d minus y is the error for a particular pattern. So if this is the ith pattern, like in the slide it is shown as the ith pattern, So for each pattern, we are making some error. Sorry. So IS pattern, we are making some error, first, second. So likewise, we have n different patterns. It is n different patterns. So we are making n different errors. Now, how these errors can be used to update the free parameters of the network. So for that, we have several algorithms, different types of algorithms. So one of them, which comes under this category, unconstrained optimization techniques. So we want to adjust the parameters such that the error reduces. If next time. Achha. So for that, let us consider a cost function CW. C is a function of weight that is continuously differentiable of differentiable with respect to W. Okay, so we were talking about the error at the output of the adaptive filter. So now from this error, if we are able to come up with some function C. So what is error E is D minus Y that we have written, and Y is summation of xi wi. Okay, so from this E is used to compute some cost function. How it is computed, that is not stated. Some cost function C. This error. What is C? Only thing that is given is C is continuously differentiable. So C cannot be some function like mod x or something which is non-differentiable function. So C is a continuously differentiable with respect to W. Why W? As you can see, E is a function of W here. Wi is there. So if C is computed from E, C is also a function of W. So let's say we know how this function C is defined. If we know this thing, let's say, if we have single weight, let's say we have this function plus 5W square plus 7W plus. So this is a continuously differentiable function. So if we have this information, then how we can do the optimization? Let's see that. So this W we consider as single dimension. It can have two components also. Like depends on how many inputs we have. If we have one input, then we have a cost function like this. If we have two inputs, then we can write some cost function like this, etc. So 7W1, W2. But only thing that is stated is C must be continuously differentiable with respect to W. Okay. So function CW maps. So if we are able to, if we have this function, how C varies with respect to W, we can easily plot that for each value of or each W. W is a vector in general case. So W1, W2, M components for a particular point, W1, W2, W1, what is the value of C? So that we can get from the function. So what is our task? Our task is to find the minimum value of C. Let's say how C varies with respect to W, we know that. If we consider say single dimensional one input only, C varies with respect to W something like this. It is a continuously differentiable function. So we want to get to this point. So at what value of W, say W star, C is minimized. So if C is minimized, then at that point this error for each pattern will also be minimized. So this is the objective. At which value of W, C gets minimized. Okay. So this is a difficult problem because it can be solved with maxima minima definitely if we know the expression for C. But in if we want to go for AI based method, that is heuristic approach. So how to choose this parameter W? So we use some intuition here. What intuition we choose? We say, let's say we initialize the system randomly. Let's say we are at some weight here, W. So that means the value of C is somewhere here at that point. So if we will say, I mean, what unconstant optimization techniques, we are saying that if we are able to change this weight such that the value of C reduces after changing the weight. So if we select some weight here, let's say this is the weight at the next iteration W1. So value of C is less than my current value of C. This is my current value of C. This is my next value of C. C1 is less than C. So if this happens, then we can at least guess that we are going towards the optimal solution. Like every iteration, if the value of C reduces. So we need to, okay. Yes. So starting with some initial parameter vector W0, that is my current weight. If we are able to generate a sequence of parameter vectors, so after every weight update, W0 becomes W1, next W1 to W2, etc. It goes on. So if it reduces the cost function value, that is cost function value for W1 is less than cost function value for W0. Cost function value for W2 is less than cost function value for W1, and so on. If this continues, or if this happens, then we can hope, we can guess that the algorithm is going towards the optimal solution. That means we are going down the cost function, and finally we will be able to reach the actual optimal solution, W star. So this is only a hope. It's this what is very important. We are not writing, we guarantee. We hope that the algorithm will converge. So why we cannot guarantee? Because we are taking the decision at this current point. Okay, if we move in this direction, cost function value is reducing, but we do not know what is the how this cost function shape will become, I mean, after this point. So for example, if my cost function shape is like this, so when I am going from here to here, so cost function value is reducing, that is fine, but actually I am not going towards the optimal solution here. So if I select this weight, then probably I will be able to reach the actual optimal solution. So always it does not guarantee that we will get the actual optimal solution. We can get stuck at local optimal solution also. So that's why this what is written, we hope that the algorithm will converge to a local optima. Okay. And what is the necessary condition? This we all know from our knowledge of maxima minima, grad C, that is the gradient at this point is 0. So if you are able to draw the gradient, it is parallel to W axis. So grad basically, when we think of multi-dimension, grad C is basically, we differentiate it, partially differentiate with respect to all the components. The cost function C. If we have m components, we differentiate with respect to all the m components, that is grad C. So we will learn 3 different techniques to solve this unconstant optimization problem. The first one is method of steepest descent. So what method of steepest descent says, successive adjustment. So it states some rule here. The rule is given in bold. That is, the weight at next step will be my current weight minus some positive constant eta multiplied by Gn. Gn is the gradient of the cost function at my current point. So that is, gradient means the direction along which the function is changing the most. Okay, so we will move in the direction opposite to that gradient. So if gradient is pointing upwards, we will move downwards. So that's why this minus sign is coming. And how much downwards we will move, that is controlled by this parameter eta. So eta is a positive constant. It is called learning rate. And Gn, gradient, is basically grad of CW. So we are differentiating with respect to all the components of W. So with this weight update rule, method of steepest descent says that if we apply this rule to the adaptive linear filter, then we will be able to learn some linear function using the adaptive filter. Okay, so eta is, this is called, symbol is called eta. It is a positive constant called learning rate or step size parameter, and Gn is the gradient vector at my current point. So evaluated at Wn. Okay, so now why we said that in this slide we said that at each iteration, if we can show that the cost function value is reducing than my previous value, so then we can hope that we are going towards the optimum solution. So now with this weight update expression, can we prove that? So if this is the weight update expression which is given by the method of steepest descent, so can we prove that the cost function value will reduce if we change the weight from Wn to Wn plus 1? We can actually prove that using Taylor series expansion. So Taylor series expansion up to first order term. So if you see this first line, C of cost function value at Wn plus 1, that is after updating the weights, can be written in terms of cost function value, previous cost function value, that is at the previous weight, that is Wn, plus this is the gradient multiplied by delta Wn. This is from Taylor series expansion. The second term will have some quadratic function of W. This is linear function, then quadratic function, and this will be second derivatives of cost function. So this is up to first order term. If we expand, then sorry, this is nothing but the gradient of the cost function, grad C W. So this is gradient of the cost function. We are writing it as Gn. This is C, grad C, we are writing as G basically. So Cwn plus 1 equals to Cn minus eta G transpose n, because we have said by method of steepest descent is saying the change in weight is Wn plus 1 minus Wn. This is the change in weight, delta Wn, which is equals to minus of eta Gn. So if we just put it here, this delta Wn is minus eta Gn and grad C is basically Gn. So we are getting G transpose n Gn, which is the squared Euclidean norm of, or the squared magnitude of the gradient vector. So now we said eta is positive constant, Gn magnitude is also positive. So this whole term eta multiplied by this Euclidean squared norm of Gn must be a positive quantity because eta is positive. So we are subtracting a positive quantity from Cwn. So therefore Cwn plus 1 definitely must be less than Cwn. Okay, so the algorithm converges to the weight vector W star slowly. So we have to repeat this weight update process for multiple iterations so that the algorithm gradually converges. But this convergence behavior is guided by this parameter eta. It has a huge influence on how the model is learning or how much the model is learning. So we said eta is, till now we have said eta is a positive constant, but what will be the range for eta? What is the range of values for eta? So there are different cases. Let's say eta is very large. When eta is very large, so let's say very large means we are talking about some eta which is close to 1. What will happen if the eta is more than 1? That we will gradually discuss. So if eta is close to 1, then what happens is this eta, we are every time we are changing the weight by the value of Gn. So eta is close to 1. So Wn minus Gn basically is Wn plus 1. So we are updating the weight by a large amount. So what can happen? So the transient response of the algorithm, it becomes oscillatory. It follows a zigzag path. So if we, this diagram we can explain in this way. So basically we have drawn this diagram some time back, that if cost function, how cost function is related to W. We have drawn such diagram. So if we consider, let's say, two components for W, so W1, W2, so this, it will be something like this. It is a 3D shape, and if you view it from the top, so if we place our eye here, so we can see the concept. I mean, it is a circle. So I mean, if we just see the circumference of this surface, so these are some circles, right, or ellipse, whatever, depending on the shape. So this diagram basically shows the top view. So we are just drawing these circles. What can happen for I mean, if eta is very large, we are starting with, say, this weight vector. This weight, the cost function value is this. Next, we change the weight to this point. So cost function value is this. Then we again change the weight to this point. Cost function value is this. So there is a huge jump. So this trajectory traced is very, I mean, it's a zigzag pattern. Whereas if we have this thing is also called underdamped situation. So there is no damping. It is freely moving. That the particle is moving freely, basically. So underdamped situation. Whereas if the eta is very small, that is close to zero, if eta is very small, then this convergence behavior is very smooth. That is, it gradually slides down the surface of the cost function, and it settles at the I mean, optima. Okay, so this particular case is called overdamped situation. Overdamped means we are putting lot of damping. It is unable to oscillate freely. It is moving in very small steps. Okay, so this is overdamped situation. It is very large is underdamped situation. But very large, we said it is close to 1, and very small means it is close to 0. What if eta is more than 1? If eta is more than 1, then what will happen? Let's see, if we apply Taylor series expansion here, as we can see, expansion is up to first order term. So there are second, third, fourth, fifth. I mean, it is an infinite series, right? So second order term we have not considered here. We have ignored second order term. When we can ignore that? If it is very less. If the value is very less, second, third, fourth order term, then only we can ignore that. Why we are ignoring? Because we are considering, I mean, this eta is between 0 to 1. If eta is greater than 1, then in the second order term, what will happen? I mean, it will become like this, delta, this is the second order term. Sorry, this plus is not there. Okay, sorry. Plus, no? So Wn. So Hn is the matrix of second derivatives, which is multiplied by the weights 2 times, and 1 by 2 factorial is obviously there. Then third term will be 1 by 3 factorial. This will have 3 times. Third derivative of the cost function will come into play. So since delta Wn is minus eta of Gn, that we have shown, I mean, this is method of steepest descent. So delta Wn 2 times, it's multiplied. So eta square will come. In this term, eta cube will come. Then eta to the power 4 will come. So if eta is greater than 1, we could not ignore these terms, basically. We have to keep these terms. So method of steepest descent works only if eta is between 0 and 1. So that Taylor series expansion can assure that yes, cost function value is reducing after each weight update. Okay, any question up to this point? Any questions? No. No questions? Okay, fine. So let's continue. So next, on constant optimization technique, the problem is same. So we have a cost function which varies with respect to weights. We know the expression of C with respect to W, and we are trying to find the minimum for which W cost function minimizes. So the first technique we studied is method of steepest descent. The second technique we are studying is Newton's method. Okay, so here this Newton's method is based on minimizing quadratic approximation of the cost function. In that means here quadratic approximation means we have to compute second derivatives of the cost function. In method of steepest descent we had gn, which is the first derivative of the cost function. Here we need to compute second derivatives as well. So minimization is performed at each iteration of the algorithm. It is okay. So using Taylor series expansion, again Taylor series expansion we are applying here. How the cost function after updating the weights is related to the previous cost function. So that is given by this expression. So in a method of steepest descent we considered the first term only. We expanded up to first order term. Here we are also adding the second order term, because it works by minimizing quadratic approximation of cost function. So what are these terms? So delta W transpose N is the change in weight, and delta Wn is also the matrix of change of weight. Hn is matrix of second derivative. It looks like this. So basically the second term, if we see, half delta W transpose N Hn delta Wn. So if we just think as say two components, that means the unknown that adaptive filter has two inputs, so two weights W1 W2. So these are the two weights. Then how this term will look like? Half of delta W1, that is how much W1 is changed, how much W2 is changed. So we write Wn plus 1 minus Wn. This is delta W. So this is vector. So every component W1 delta W1 is the change in weight of the first component. Delta W2 is the change in weight of the second component. I'm not writing all. So next Hn is the matrix of second derivative. So basically del 2c, del W1, del W2, and so on. So it is a square matrix, M cross M matrix. If there are M components, then Hessian is a square matrix. So second line it will be del W2, del W1, then del 2c, del W2, del W2 2. Then last component is del W2, del Wm. It is given in my slide, so better I can show that. So this is Hessian matrix. So M cross M dimensional. And the important property of, using calculus properties, we can say that this is symmetric matrix. That is, its transpose of the Hessian matrix is also Hn. So basically, if you differentiate C first with respect to 2, then respect to 1, it is same as if we differentiate C first with respect to W1, then with respect to W2. So it is a symmetric matrix. So now this cost function, change in cost function is this. So now at optimum value, what happens? At the optimal value, say the change in cost function. So if this is the cost function, this is weight. So at the optimum point, so the change in cost function with respect to change in weight, that is delta C, delta W, this is minimum. So change in cost function with respect to change in weight is minimum. So we differentiate this delta CW. So this is change in cost function. The change in weight is delta W. So if we do this differentiation, we get these terms basically, that Gn plus Hn. We can do this derivation. It's very simple. So differentiating this term, this delta C of Wn with respect to delta Wn and equating it to 0. That's how we do maxima minima. We get Gn plus Hn delta Wn equals to 0. So that means the I mean, derivative of this first term with respect to delta Wn is Gn, derivative of this second term with respect to delta Wn is Hn multiplied by delta Wn. We can easily prove that. So we get Gn plus Hn delta Wn equals to 0. From here, we get the weight update expression, that is delta Wn is minus H inverse N multiplied by Gn. That means if we know the cost function value, if we know the cost function C with respect to W, from there we have to first compute the Hessian matrix, and we can also compute the gradient at the current point. If we multiply this inverse of the Hessian matrix with gradient and put negative there, so that is the change in weight. Okay, any question? Any question? So, okay, fine. So, now, I mean, again, if we want to, any questions? So, previously we have shown that for method of steepest descent, the weight update rule that is given Wn plus 1. What is the weight update rule for method of steepest descent? Wn plus 1 is Wn minus eta Gn, right? So this is method of steepest descent. And this is method of steepest descent. I am writing MSD. Our Newton's method is saying Wn plus 1 equals to Wn minus of H inverse N into N. Okay, so this is the Hessian matrix inverse and this is the gradient. This Gn is there, but we need to do this additional computation. So what are the main differences? This method of steepest descent says function C must be differentiable with respect to W, and Newton's method requires C must be twice differentiable because we are computing this Hessian matrix with respect to W. And these are the two weight update expressions. So we can use either of these to train adaptive filter. But in general, we observe that since this depends on eta, so if eta is very small, convergence is bit slow. And here there is nothing eta in this Newton's method. So this converges very fast basically. So if we start with any random weights, and if we apply this weight update rule, we will get too close to the optimal solution in one step almost. We may need to apply one more time, but we will go very quickly to the optimum solution. But for Newton's method to work, this is another important point. This matrix must be positive definite at every iteration of the algorithm. So if it is not positive definite, then Newton's method cannot be applied. Basically, we can prove this. I mean, I am not going into the proof. So this positive definite means its eigenvalues are all positive. So what happens if eigenvalues are positive, then that function minima. If there are no positive eigenvalues, function does not have any minima. Okay, so we want to find the minimum value of the cost function. So Hessian matrix, the cost function shape should be such that the Hessian matrix is positive definite. And here also we can prove this thing. If this is the weight update rule, then C of Wn plus 1 is less than C of Wn. We can prove that. If we just substitute delta Wn equals to minus H inverse N Gn. So we got this weight update, I mean this change in cost function expression. So in place of delta Wn, if we just put minus H inverse N Gn, here also we put that, we can show this thing. It's like 2-3 steps, we can show this thing that cost function after updating the weights is less than the cost function before updating the weights. Okay. Any question up to this point? Right. There's some noise is coming. Someone is unmuted, I think. Any questions? Any questions? No questions? Okay. Okay. So, I mean, we have one more unconstrained optimization technique. It is called Gauss-Newton's method. Currently, we are skipping that. I mean, we are going directly to the last method, which is called the least mean square, which is most important, and we apply it most often in our works. So this is called the least mean square algorithm. Okay, so what it says, previously, if you remember, I mentioned the point that from every pattern we can compute some error E, and from that error E somehow we compute a cost function. That how from error E we compute the cost function we did not discuss. So cost function is any function of W, any function of error. So now least mean square algorithm specifies this is the cost function expression, that CW equals to half of E square N. So whatever error we are making at the output, if we square that up, half is basically useless here. Like we have to do some derivative later. This E square N 2 comes and half gets cancelled. These two gets cancelled. That's why half is added. But as such, it has no physical significance. So minimizing E square N is equivalent to minimizing half E square N. That's why this half is written. So least mean square algorithm has another name also, that is called stochastic gradient descent. Previously, we have learned method of steepest descent, and this is stochastic gradient descent. These two are very similar, but there are some differences. What are the differences? Method of steepest descent says cost function must be a linear, some continuously differentiable function of W. Stochastic gradient descent says that cost function should be related with error function in this way. That is, we will find the error at the output of the filter, square it up, and divide by 2. Okay. So if this is the cost function, then what is the gradient of the cost function? So at that point, one thing, I mean, we have to understand that previous two cases, Newton's method and method of steepest descent, assume that the cost function expression is known. How C varies with respect to W, that is known. That means the function of, the C as a function of W, say some half W cube plus 7W square, etc., 8. So some function about C is known. But if we look into real life situations, where when we deal with a classification or real life problem, we have only some data. We do not have any expert who can give us this how C varies with respect to W. So whatever we have studied till now, method of steepest descent, Newton's method, these are mathematical concepts, but in practically we cannot apply them directly. What we can do, again, we can try to estimate some cost function value at my current weight. So now we are, let's say we are at somewhere W1, W2. So this is two components are there. This is the cost function, which we do not know. Now we do not know how C is related with respect to W. But what we can do, okay, for this W1, W2, what is the cost function value that we can try to compute using this expression? But we do not know the entire shape of the cost function. So previous logic, their cost function must be differentiable with respect to weight does not apply for this stochastic gradient descent. So this is an instantaneous error. We have fed some pattern and we have computed some error E, from which we are computing some instantaneous value of the cost function C. Achha. So other expressions are very similar. So gradient is del C del W. We have studied grad C in method of steepest descent. Basically, this is grad C. So del C, this is chain rule of differentiation. If we follow this logic, del C del E is En. From here, 2 gets cancelled, En comes, and del E del W is Xn. How it is Xn? Because you know error is minus Xn. Basically, error was desired output minus predicted output. So this Y is basically X IWI. So here we are getting Xn, that X is coming here with a minus sign, del E del W. This is used as an estimate. So this is, since we do not know the actual cost function, we cannot compute the actual gradient vector. So this is an estimate of the gradient vector at my current point. So estimated value is minus En Xn. Now, since method of steepest descent, we know the cost function is, how weight update expression is given, Wn plus 1 is Wn minus eta del C del W, or eta of gradient, multiplied by gradient at the current point. Here we have made an estimate of the gradient, that is minus x into E. So eta minus xe, this gets multiplied with eta, so Wn plus eta, x is at the current iteration, xn multiplied by En basically. So this is the weight update expression for stochastic gradient descent or least mean square algorithm. So it is very similar to method of steepest descent, but look wise it's similar, but actually it is very different. So how, and this algorithm we use to, in any neural network training nowadays, like either multi-layer perceptron or deep learning, whatever. So what is the algorithm? If input signal is xn, desired output dn, we select some parameter eta, that is the learning rate. We discussed about learning rate eta. Then we set some initialized weights w naught to 0. It need not be initialized to 0, it can be any random value. The initial weights are set to any random value. Then we go for multiple iteration. We feed every pattern. We compute some error using this term dn minus w transpose n xn, and then we apply the stochastic gradient descent expression. Whatever error we are making, we are updating the weights. Okay. So this is how LMS algorithm works. We can use LMS algorithm to learn and function, any function that is linearly separable, any classification or regression problem where we need to draw a straight line, that we can try to learn using this stochastic gradient descent. Okay, but if we have to learn a nonlinear separator, then this is not the algorithm to go for. Then we go for the higher version, an improved version of single layer perceptron, which we call as multi-layer perceptron, that we are going to discuss in our next session. So if you have any questions, you can ask. And now, if anyone has any questions. Hello? Anyone has any questions?
No, sir.
Tell me. Okay. So we can close the meet today. Tomorrow again we will meet. Anyone is there from TLC? So can we close the meeting now? Okay, then thank you for attending. So we will meet again tomorrow. Okay, if you have any questions, you can ask me via email. I am writing it, my email here.
Sir, am I audible? Sir, please share your PPT. Most of the speakers, they promised to share their PPT, but we have not received.
To whom I will share, how I will share that? So in that email
Yes, sir. That is a request from me also, sir. Please share the PPT, sir.
ठीक ठीक
Sir, if you will provide your number, so maybe we can send in WhatsApp message, and with that particular
Now
WhatsApp message we can
today
share in the
from
group.
TLC one email came to all of us, so I am replying to that. Okay, that will be better now.
Which email ID, sir?
One email came from office of TLC today.
Okay, sir. We'll take your email ID from here.
I am replying to that. So I think all of you will receive there. I am sending it right now.
Okay, sir. Thank you, sir. Thank you very much.
Okay, thank you.
Thank you, sir.
I am leaving. Any questions? Any questions? Okay then. So.